Welcome back to Introduction to Software Reverse Engineering. In our first video, we explored the practical need for reverse engineering and some aspects of it, its significance in the field of computer security, and its impact on innovation. Today, we are going to dive deeper into important technical details of CPU architectures and a number of conventions adopted over the years in computer industry to facilitate development of software and data processing and exchange systems. Let's get started. All right, let's get specific about what we'll cover in this module on computer programming fundamentals. We are going to review some low-level aspects of CPU architectures that are directly related to reverse engineering, as well as conventions when it comes to running software on x86 platform. The scope includes Endianness. We'll explore the difference between little endian and big endian architectures and how data is represented in memory. You'll see how this impacts the way code is written and executed. Program memory model. We'll discuss how memory is organized and allocated for programs, including the different segments and their purposes. The stack. A crucial data structure in programming. We'll cover how the stack works, how functions use it, and why it's important for understanding code execution. Assembly and C programming languages. We'll focus on these two languages, exploring the basics of assembly language and how it relates to C programming. You'll see how understanding assembly code can help you reverse engineer binaries. By the end of the module, you'll start gaining an understanding of the low-level details that underpin programming. This foundation will serve you well as we dive deeper into reverse engineering and analyzing code. Now that we've covered the basics, let's focus on the specific type of programming we'll be dealing with in this course. This course is about 32-bit x86 Intel and AMD CPUs. The x86 architecture is one of the most widely used architectures in personal computers and servers. The x86 architecture has a rich history, dating back to the Intel 8086 and 8088 processors. Over time, it evolved from 16-bit to 32-bit and eventually 64-bit instruction sets. In this course, we'll be focusing on the 32-bit aspects of this architecture. Throughout the course, we will cover x86 instruction set focused on integer computation, as well as x87 instruction set developed for floating point number computations on the CPU. By understanding the x86 and x87 instruction sets, you will be able to understand how the code is executed at a low level. This knowledge will serve you a solid foundation for your reverse engineering endeavors. In the world of computer memory, a fundamental concept shapes how data is stored: endianness. This refers to the order in which bytes are arranged for multi-byte data types like integers and floating point numbers. Two dominant approaches have emerged: big endian and little endian. Big endian systems prioritize the most significant byte, storing it first. This sequence made it intuitive for humans to read the data from left to right, mirroring the way we typically read text. Big endian structured approach has made it a staple in networking protocols like TCP/IP, where it's known as network order. In contrast, little endian systems take a different track, storing the least significant byte first. This arrangement suits certain computational tasks and has become the norm in most PC architectures, including the widely used x86 architecture. Understanding endianness is crucial for developers working with low-level data representation, as it directly impacts how data is stored, transmitted, and interpreted across different systems. When working with binary data, understanding endianness is crucial. Endianness refers to the way a computer stores multi-byte data types, like integers or floats, in memory. Imagine you're working with a 32-bit integer. In big endian systems, like those using PowerPC or SPARC processor architectures, the most significant byte of the integer is stored first. This is also the case in some ARM CPUs and in the TCP/IP data communications. Think of it like writing a date in the format year, month, date. The most significant part comes first. On the other hand, in little endian systems like x86 and x64 processor architectures, the least significant byte is stored first. Some ARM CPUs also support little endian byte order. It's like writing a date in the format day, month, year. The least significant part comes first. But here's the interesting part. Some CPUs are bi-endian, meaning that they can be configured to use either a big endian or little endian byte order. This flexibility is useful in certain situations, like when working with data that's being transmitted over a network or when dealing with legacy systems. As a reverse engineer, understanding endianness is essential to accurately interpret and analyze binary data. Endianness plays a critical role in various aspects of computing, including data storage, transmission, and processing. Let's explore its importance in different areas. When exchanging data between systems, endianness can significantly impact how binary data is interpreted. Ensuring correct interpretation between systems with different endiannesses is crucial for maintaining data integrity. In network communication, protocols like TCP/IP use big endian byte order. When working with little endian systems, conversion might be necessary to ensure seamless communication. Endianness also affects how binary data is stored in files. If not interpreted correctly, it can lead to errors. Understanding endianness is vital when working with file formats that store binary data. In programming, endianness is essential when working with binary data, pointers, and memory management. It can impact the correctness and reliability of software. When developing software for multiple architectures, endianness differences must be considered to ensure compatibility and accuracy. If endianness is not handled correctly, it can lead to data corruption, errors, and potentially even security vulnerabilities. By understanding and addressing endianness, developers can ensure that their software works correctly and efficiently across different systems and architectures. When a program runs, its memory is organized into distinct sections, each with its own purpose. Understanding this memory layout is important for reverse engineering of binaries. Let's break down the main memory sections. The text section contains the executable code, which is the compiled program logic. The data section stores initialized global and static variables, which retain their values throughout the program execution. The heap is used for dynamically allocated memory, where the program requests memory at runtime. The stack stores local variables, function parameters, and return addresses, which are essential for managing function calls and returns. The C memory model defines how memory is allocated, accessed, and managed for different types of data and program components. Let's take a closer look at the different program memory sections. The text section contains the machine code instructions that make up our program. This section is typically read-only, meaning its contents cannot be modified during execution. The data section stores global and static variables that have initial values. Unlike the text section, the data section is a read-write, allowing its contents to be modified as the program runs. The stack section is used to store local variables, function parameters, and return addresses. It follows a last in, first out, or LIFO structure, meaning the most recent items added to the stack are the first ones to be removed. The stack section is also read-write. Finally, the heap section is used for memory allocated at runtime using functions like malloc or realloc. Unlike other sections, memory management on the heap is implemented by the software engineer, requiring careful allocation and deallocation to avoid issues. The heap section is typically read-write. Let's explore how the stack and heap grow in memory. The stack grows from high memory addresses to low memory addresses. As the new stack frames are added, the stack pointer moves downwards in memory. This means that the stack starts at high addresses and expands downward as more functions are called and local variables are allocated. In contrast, the heap grows from low memory addresses to high memory addresses. As more memory is dynamically allocated using functions like malloc or realloc, the heap expands upward in memory. This opposing growth pattern allows the stack and the heap to coexist in memory, with the stack starting at high addresses and growing downwards, and the heap starting at low addresses and growing upwards. Let's explore the different computer programming languages. At the lowest level, there are machine codes. This is the language that computer's processor can execute directly, consisting of binary code representing a series of zeros and ones. The processor understands and executes this code without needing any translation. Next, we have low-level languages. These languages provide direct access to computer hardware resources, such as memory, registers, and input-output devices. Examples include assembly languages, which are specific to a particular computer architecture. Finally, we have high-level languages. These languages provide strong abstraction from the details of the computer's architecture or capabilities. Examples include languages like C, C++, Rust, and Zig. High-level languages are easier to read, write, and maintain, and they are often used for complex applications and systems programming. Assembly language is a family of low-level programming languages that use symbolic representation of machine code instructions. This allows developers to write code that directly interacts with computer hardware. Assembly language is particularly useful in certain scenarios. For example, it's often used in the development of embedded systems, where resources are limited and efficiency is critical. It's also used in operating system development, where direct access to hardware resources is necessary. Additionally, assembly language is used in device driver development, which requires direct interaction with hardware devices. It's also used to optimize performance-critical code, such as in games or scientific simulations, where every cycle counts. By using assembly language, developers can fine-tune their code for maximum performance and efficiency, making it an essential tool in certain domains. High-level languages are programming languages that provide strong abstractions from the details of the computer. They allow developers to focus on the logic of their program without worrying about low-level details like registers, memory addresses, and call stacks. Instead, high-level languages deal with abstract concepts like variables, arrays, objects, and functions, making it easier to write and maintain code. They are designed with usability in mind, prioritizing ease of use and productivity over optimal program efficiency. Examples of high-level languages include C, C++, C#, Java, Rust, Zig, PHP, and JavaScript. These languages are widely used for building complex applications, web development, and more, thanks to their flexibility, expressiveness, and ease of use. C is a general-purpose programming language that has been widely used and influential since its creation in the 1970s by Dennis Ritchie. One of the key aspects of C is its balance between low-level and high-level features. On the low-level side, C provides direct memory access, allowing programmers to manipulate memory addresses directly. It also supports bitwise operations, enabling the manipulation of individual bits. Additionally, C doesn't perform runtime checks, giving programmers fine-grained control over memory management. On the high-level side, C provides abstractions like structures, unions, and functions, which simplify programming and improve code readability. C code is also highly portable, meaning it can be compiled on various platforms with minimum modifications. Furthermore, C has a type system that helps catch type-related errors, making it easier to write robust code. This unique blend of low-level control and high-level abstractions has made C a popular choice for systems programming, embedded systems, and other applications where performance and efficiency are critical. When it comes to reverse engineering, C is an ideal language due to its unique characteristics. As an imperative procedural language, C has a static type system and supports structured programming, lexical variable scope, and recursion. Its design allows for compilation to machine code that provide low-level access to memory and efficient mapping to machine instructions, all with minimal runtime support. These traits make C a perfect fit for reverse engineering. Its low-level nature, portability, flexibility, and performance make it an ideal language for working with machine code. Additionally, C's close ties to hardware make the reverse process of interpreting machine codes back into C possible. Tools like Ghidra take advantage of C's characteristics, decompiling binaries into C-like code, importing C headers, and containing a large library of native platform-dependent types and structures. This makes C a fundamental language in reverse engineering, allowing engineers to analyze and understand binary code in more human-readable form. Throughout this course, we will be exploring a range of C programming examples that will serve as a foundation for our journey into reverse engineering using Ghidra. By deconstructing and analyzing these programs, you will gain a deep understanding of Ghidra's decompilation output and learn to correlate it with the original C code. The goal is to develop the skills necessary to proficiently reverse engineer complex software systems. By the end of this course, you will be equipped with the knowledge and expertise to tackle real-world reverse engineering challenges. If you are interested in following along or referencing the course materials, you can find them on GitHub at the link provided below. Let's get started and dive into the world of reverse engineering with Ghidra. If you are looking to dive deeper into software reverse engineering, I'd like to recommend my book, Software Reverse Engineering: Navigating x86 Windows Applications with Ghidra. This course draws heavily from the book's content. However, the book itself contains many more examples and insights that can help developing your reverse engineering skills. The book is available in both print and digital Kindle versions on Amazon, making it easy to access and read wherever you are. Additionally, the book covers subjects not discussed in this course, such as reverse engineering of C++ programs, classes, virtual functions, and more. I encourage you to check it out. Thank you so much for watching and learning with me today. If you found this video helpful, please hit that like button and subscribe for more content like this. Your support means a lot to me. If you have any questions or topic you'd like to discuss, leave a comment below or shoot me an email. I'm happy to chat. If you'd like to support me and the channel financially, you can do so through Ko-fi or Patreon. Links are in the description below. Thanks again for watching, and I will see you in the next video.